Right now, while every camera on Earth is pointed at Japan, a fault most Americans couldn't name has moved for the second time in 5 weeks, and almost nobody noticed. The United States Geological Survey logged more than 160 seismic events tied to it within hours and flagged the trigger quake as a potential main shock. That single word, potential, is doing more work than almost any word in modern seismology because it means the agency itself does not know yet what this is. This fault runs directly toward the Bay Area, and its buried history holds ruptures far larger than anything in its short modern record. Here's what it's done before. What happened? 3 time zones away on the same day, and the one signal that will tell us what happens next. The ground broke at 7:40 and 6 seconds on Tuesday evening, Pacific time, 5 miles east-southeast of Cloverdale, California. USGS put the magnitude at 4.3, revised up from an initial 4.2 within the hour. The depth came in around 5.5 kilometers, barely 3.5 miles down, which in earthquake terms is almost skin deep. The Northern California seismic network puts it a touch deeper, closer to 6 kilometers. Either number lands the rupture inside the shallow, brittle upper crust, the layer where shaking hits hardest for the energy actually released. Nobody was hurt. Nothing collapsed. The USGS's automated impact system issued the lowest alert level on its scale, green, for both casualties and economic loss. More than 520 people filed felt reports, close in from Healdsburg, Geyserville, Middletown, and Kelseyville, and from as far as Roseville, Elk Grove, and San Francisco, over 60 miles out. Peak shaking reached intensity 5 on the modified Mercalli scale, the kind of shaking that rattles dishes and knocks pictures crooked, not the kind that drops buildings. On an ordinary week, a magnitude 4.3 in wine country is a footnote, a paragraph, a shake map, gone by the next news cycle. This one isn't behaving like a footnote, and the reason has nothing to do with how hard the ground moved. It has to do with what came after it. Within hours, the USGS's earthquake sequence product didn't just log the Cloverdale quake as an isolated event. It classified it as the potential main shock of an active sequence, one that had already produced upward of 160 associated events. That number is the real story here. Aftershock productivity scales with the size of the triggering quake, and the textbook expectation for a magnitude 4.3 is a small, quiet population of aftershocks, maybe a dozen, fading out fast. A sequence in the hundreds is not that. It's a signature of high productivity, And high productivity tells you something specific about the rock underneath. When one locked patch on a fault slips cleanly and settles, you get a short, thin aftershock tail. When a broad volume of crust is already sitting close to failure and one piece of it lets go, the redistributed stress lights up everything nearby. 160 events in hours isn't one patch failing. It's a section of crust actively renegotiating its own equilibrium. The USGS forecast attached to the sequence goes further, estimating at least one magnitude 3 or greater aftershock within the following week. That window opened Tuesday night, and roughly 5 days of it are still live as of this writing. None of that would carry much weight if it happened on a fault nobody could place on a map. It didn't. The Cloverdale epicenter sits on the Makama Fault, a structure that lives entirely outside public awareness, despite doing real work on the plate boundary. The Makama is a right lateral strike-slip fault trending northwest to southeast through the North Coast Ranges, east of the San Andreas, dipping somewhere between 50 and 70 degrees to the east. It carries a meaningful share of the motion between the Pacific and North American plates in this part of the state, motion the San Andreas alone doesn't fully absorb. Its slip rate sits around 9 millimeters a year, give or take 1.5 millimeters per the deformation model built for the 2023 National Seismic Hazard Model.
Is doing real work. It is not the sound of magma breaking through toward daylight. It is the sound of a reservoir slowly refilling deep down, pushing gently against rock that has held it in check for years. The earthquakes are a symptom of feeding, not of an imminent eruption, and that distinction is the single most important idea in this entire story. It helps to actually sit with how small these earthquakes are. Magnitude is not a straight ruler where each number is a little more than the last. It's closer to a set of stairs, and each full step down represents a massive drop in the energy released. A magnitude 1 earthquake is not a slightly gentler version of something you'd notice. It is thousands of times fainter than a quake that would rattle a coffee cup. These are events that exist as squiggles on sensitive seismometers and nothing else. You could stand at the exact point on the mountain directly above one of these quakes and feel nothing at all. That's the scale being discussed here. Dozens of whispers rising from a reservoir several miles down. Not a single shout from magma breaking the surface. And the location of these quakes matters far more than the raw count. 100 faint whispers originating 2 or 3 miles underground tells a completely different story than a handful of sharp, shallow cracks a few hundred feet beneath the crater floor. That distinction, depth, and location is the line between a routine week at a living volcano and an actual emergency. And it's exactly what the monitoring network is built to track. Naturally, a gap has opened up between what official catalogs report and what independent seismology enthusiasts claim to see when they pull up raw, unfiltered instrument traces. Every time a swarm like this happens, someone points at the raw wiggles on a seismograph and says, the true number of quakes is far higher than what's been officially logged, and that agencies are quietly sitting on the difference. It's worth explaining clearly why that gap exists, because it is not a cover-up, it's arithmetic. For an earthquake to be formally located and added to a public catalog, the same signal generally needs to be detected clearly at multiple stations and triangulated to a point in space within a tight margin of error. A micro-event too faint to register cleanly at more than one station simply cannot be located with confidence a genuine whisper, then manufacture a false one. If this current swarm feels unprecedented, it's worth knowing St. Helens has essentially 46 years ago. Mount St. Helens killed 57 people in the worst volcanic disaster in American history. Now scientists are watching it again, and this time the reason isn't as simple as a shaking mountain. It's a mountain sending two signals that seem to contradict each other. One says the volcano is feeding. The other says it's settling down, not swelling up. That combination has geologists checking their instruments twice a day instead of once a week. In the next few minutes, you'll learn exactly what has scientists concerned, what it doesn't mean yet, and how you can read these signals for yourself the next time this mountain makes headlines. Mount St. Helens sits about 96 miles south of Seattle, close enough to a major metro area that when this volcano moves, it doesn't stay a regional story for long. It is the most active volcano in the Cascade Range, the same range that includes Mount Rainier, Mount Hood, and Mount Baker. And of all of them, St. Helens is the one with a body count, the one with a national monument built around a blast zone, the one whose name alone still means something to people who weren't even alive in 1980. So, when seismic instruments start logging clusters of small earthquakes beneath it, nobody in the volcanology community treats that as background noise. They treat it as homework. The current concern traces back to a swarm of small, shallow to moderate depth earthquakes registering beneath the summit and the area just north of it. The same general zone that produced the mountain's last two eruptive episodes. Individually, these quakes are unremarkable. Most sit below magnitude 1, the kind of event that would never be felt by a person standing directly above it. But volcanologists don't read individual earthquakes. They read patterns. And the pattern is what has pulled this swarm out of the routine noise category and into the worth watching category. Here's the part that makes people nervous, and rightly so if you don't have the context. Earthquake swarms under volcanoes are almost always read as one thing. Magma is moving, and the ground should be swelling to match. That's the textbook relationship. Magma pushes up, rock cracks under the strain, quakes happen and the surface bulges, outward like a balloon being inflated from below. It's a clean story, and it's the story most people already carry around in their heads from watching volcanoes in movies and documentaries. What instruments on St. Helens are actually recording right now doesn't fit that clean story. The surface deformation data, collected from GPS stations, bolted into the rock and satellite radar that can detect ground movement down to a few millimeters, shows the mountain has been subtly sinking in places, not rising. So you have earthquakes, which usually means something is pushing up, paired with a surface that is doing the opposite of pushing up. That contradiction is exactly why this swarm has generated more attention than a typical background rumble, and it's exactly the kind of signal combination that makes scientists want more data before they say anything definitive. Let's be clear about where things officially stand, because headlines have a way of outrunning agency statements. As of now, Mount St. Helens remains at volcano alert level normal, aviation color code green. There is no eruption warning. No agency is forecasting an imminent event. This is not a mountain standing on the edge of a repeat of 1980, but to understand why any single earthquake beneath this particular peak draws so much attention, you have to go back to the morning that earned this mountain its reputation, because that morning is the yardstick everything else gets measured against. The reawakening in 1980 began months earlier, with earthquakes and bursts of steam after over a century of dormancy. Then came the part with no equal in the modern record. The entire north flank of the mountain began deforming outward, not settling, not sinking, bulging, as magma shouldered its way into the side of the volcano. That bulge grew at a rate of several feet per day, and over the following weeks it pushed outward hundreds of feet from the original face of the mountain. That is visible, accelerating, shallow deformation, ground swelling as magma physically climbed toward the surface, and it is the textbook precursor that today's mountain is pointedly not showing. What made 1980 an actual countdown wasn't any single number, it was the acceleration. Over roughly 2 months, the signals stacked and intensified together. The earthquakes didn't stay faint and deep. They grew and climbed toward shallower depths. Steam explosions became frequent. The bulge didn't appear overnight. It swelled visibly day after day until it was deforming faster than the surrounding rock could hold. Anyone watching the instruments that spring could see the trend bending toward failure. That is the texture of a genuine reawakening. A set of signals, all growing, all shallowing, all pointing in the same direction at once. Hold that image, because it is the exact opposite of the flat, faint, sinking picture the mountain is showing this year. On the morning of May 18th, 1980, a magnitude 5.1 earthquake shook the overstressed bulge loose. The entire north flank collapsed at once, the largest landslide ever recorded. And with the side of the mountain suddenly gone, the pressurized system inside was uncorked. It blasted sideways, flattening forest across more than 200 square miles, stripping over 1,000 feet off the summit. Ash reached hundreds of miles away by that afternoon. It killed 57 people, including a volcanologist monitoring the mountain from an observation post several miles away, a distance everyone at the time believed was safe. The observatory that watches this mountain today was built in the aftermath of that morning and carries his name. That is the weight 1980 still holds, and it's exactly why the contrast with today matters so much. Set the two side by side, because this is the whole argument. 1980 was a surface bulging outward at several feet a day. Right now is a surface sinking. 1980 was earthquakes climbing toward the surface as magma physically forced its way up. Right now is faint earthquakes miles down, where a reservoir is quietly refilling. 1980 was accelerating, shallowing, and inflating, 3 signals all pointing the same direction, all screaming upward. Right now is faint, deep, and unsettling to look at, but flat rather than trending. Everything about the 1980 signature that made it a genuine countdown is currently absent from what St. Helens is doing. That's not a guarantee about the future. It's a reading of the present, and it's the honest one. It's also worth pausing on why the public reaction to a swarm like this tends to run ahead of the science every single time. Part of it is simple pattern recognition gone wrong. People remember the footage from 1980, the bulge, the collapse, the ash cloud rolling over towns, and their brains reasonably file earthquakes under St. Helens and catastrophic eruption into the same folder. Part of it is also how information spreads today. A raw seismograph or a scientist ever will. None of that makes the concern irrational exactly. It makes it uninformed, which is a very different and much more fixable problem. The tools to actually check this story yourself are public. Seismic networks publish their earthquake catalogs online, updated continuously, and anyone can look at the depth and location of each event, rather than relying on someone else's interpretation of it. Ground deformation data from GPS stations is also public. So is gas monitoring data. The transparency that debunks the cover-up narrative also happens to be the same transparency that lets you verify everything in this video yourself, and that's worth doing the next time a headline like this one shows up in your feed. Zoom out, and none of this is really about one mountain in isolation. Mount St. Helens sits at the surface end of one of the largest geological machines on the continent. Off the coast of the Pacific Northwest, an entire slab of ocean floor, the Juan de Fuca Plate, is being forced beneath the North American continent along the Cascadia subduction zone. The same fault system, capable of producing a magnitude 9 megathrust earthquake that geologists consider a matter of when rather than if. As that slab grinds downward into the hot interior of the planet, water trapped inside the rock is squeezed out and driven up into the mantle above it. T-het water lowers the mantle's melting point. The mantle begins to melt, and the resulting magma rises. Where it breaks the surface, it builds volcanoes, and that line of volcanoes is the Cascade Range. Rainier, Adams, Hood, Baker, Shasta, and St. Helens, each fed by the same offshore engine. St. Helens happens to be the most geologically active of the group. It has erupted more often and more recently than any of its neighbors, which is exactly why a swarm beneath it makes national news, while identical activity beneath a quieter Cascade Peak barely registers outside the scientific community. The magma this particular volcano produces is also a thick, high silica type that traps gas and builds pressure rather than flowing gently, which is part of why, historically, when this system fails, it tends to fail explosively rather than pouring out in slow rivers. That combination of youth, activity, and sticky, gas-charged magma is exactly why a small swarm here draws the attention. An identical swarm elsewhere never would. The good news, if you want to actually use this information rather than just consume it, is that scientists aren't guessing about what a real reawakening would look like. The mountain has shown them before, and none of the warning signs require a crystal ball. A genuine countdown would announce itself through a specific set of changes worth knowing. First, migration. Earthquakes shifting from deep, where recharge lives, toward the surface, tracing the path of magma actually on the move. Second, a change in the character of the shaking itself, the onset of continuous harmonic tremor, which signals fluid and gas moving through the plumbing rather than rock simply cracking under stress. Third, a reversal of the very thing making this swarm strange right now. The surface would stop sinking and start rising, with measure.
Which raises the obvious question. 3 separate readings on the same plate boundary moved inside 48 hours. Did one cause the others? No, and the reasons are more interesting than a simple yes would have been. Earthquake triggering works 2 ways. Static triggering is a permanent stress change in the crust around a rupture. Powerful and well documented. But it falls off so fast with distance that it's effectively confined to within 1 or 2 rupture lengths of the source. A rupture a few dozen miles long cannot meaningfully load a fault 5,000 miles away. That stress change isn't small, it's functionally zero. Dynamic triggering works through the passing seismic waves themselves, and that mechanism genuinely can operate at global distances. It was documented most famously after the 1992 Landers earthquake, which produced measurable remote seismicity increases, including at the Geysers geothermal field. But it has a consistent signature, strongest in geothermal and volcanic areas with pressurized fluids, showing up during or within minutes to hours of the waves passing through, and overwhelmingly producing small events in places that were already critically stressed. Cloverdale ruptured about 12 hours after the Kumamoto surface waves swept past, well outside the window in which dynamic triggering is normally identifiable, and it happened on a strike-slip crustal fault, not inside the geothermal reservoir where that kind of sensitivity is highest. The defensible statement is that there's no demonstrable trigger relationship here. These are independent events. That independence is the whole point, and it isn't the comforting version of this story. If Japan didn't push California, then California moved on its own schedule from strain accumulated locally at 9 millimeters a year on a fault that produced its largest recorded earthquake 5 weeks earlier, next to a structure nobody has formally mapped. Japan, Tonga, and Northern California are 3 separate gauges on the same machine. The Pacific Plate boundary is one system in the sense that it's driven by one set of forces, loading everywhere, always. It is not one system in the sense that one segment can reach across an ocean and set off another. Roughly 62 earthquakes above magnitude 4 occurred worldwide on Tuesday, along with 14 above magnitude 5. That's a busy day. It is not an extraordinary one. Plot events at that rate across a globe, and clusters appear by statistical necessity, not by cause. So here's what to actually watch, and it isn't the next magnitude number. The diagnostic is the shape of the aftershock distribution, and it applies identically in Sonoma County and in Kumamoto. If aftershocks stayed tightly clustered around the main shock's hypocenter, that's a normal sequence decaying and releasing local stress on schedule. If they start elongating along the fault trend, northwest toward Ukiah and the June rupture, or southeast toward the Rogers Creek fault, that indicates stress transferring onto adjacent segments, and segment-to-segment progression is exactly how a moderate sequence becomes a larger one. In Japan, the same test runs along the Hinagu trend, right where the largest early aftershocks are already sitting. USGS forecast gives a concrete checkpoint. At least one magnitude 3 or greater within the Cloverdale sequence by early next week. Where that event lands on the map matters far more than whether it happens at all. For Japan, the high-risk window the agency flagged closes around today and tomorrow. If it closes without a comparable magnitude event, the 2016 pattern will not have repeated. One more thing rules out what people will otherwise reach for by default. Tectonic tremor along the southern Cascadia subduction zone was checked Tuesday evening and came back at 0 after runs of 307 epicenters margin-wide on July 14th and 382 beneath the southern margin on July 24th. Cascadia is not responding to any of this. What changed this week isn't the loading. The loading never stops on any of these faults. ever. What changed is that 3 gauges on the same plate boundary moved within 48 hours of each other, and only one of them got covered. The one nobody looked at is attached to a fault that has now moved twice in 5 weeks. That's storing more strain than its creep rate lets on, and that runs in an unbroken line straight into the Bay Area. The next 7 days of that aftershock map will tell us which kind of sequence this actually was.